Okay, this video is about unit analysis. We'll be looking at how to analyze the unit so you can check your work, what are the rules involved when we're dealing with measurements that have units with them, and what are the acceptable units for your final answers. So let me go start with that last one first. What are the acceptable units for your final answer? So all year, these are your acceptable units. Every answer should be some combination of these four: kilograms, meters, seconds, and coulombs. So if you collect data for a lab or something like that, and you're in centimeters, you got to convert it. If you're in grams, you got to convert it, so on and so forth, right? So when you're doing long kappa, when you're taking a test, when you're doing lab work, these are the units for every single answer. With that said, as we get more and more into the material, the units will get more complicated, but they will be some combination of these, right? These are our fundamental units that I'm listed on the screen. And what I mean by that is I kind of think of them as like you've learned primary colors, right? Primary colors, you have these primary colors, and you can't mix anything else to make those colors, but you could use those to make everything else. And these fundamental units are like that, right? I can't really combine anything else to make a mass, a length, a time, or a charge. But I'll use these four measurements and I'll combine them in many, many different ways to get all the other measurements that are out there in the world, right? For example, a speed is meters per second. A force is a kilogram meter per second squared, right? So as we get more and more into the topics, the units will get more and more complicated, but there'll always be some combination of these four. And that's really where unit analysis comes in. We want to make sure that when we combine units, when we're doing math, we see what the end result is, not just numerically, but the end result of the units. And then if it matches up with what we expect, we know we did it right. If it doesn't match up with what we expect, we know we're wrong, right? So we should always be confident in our answers because we're checking the units as we go. All right, so here are the rules. The first one's nice and easy. So rules for math with units. The first one is just when we're doing addition and subtraction, there's just one rule, and that's they have to be the same units, right? It's impossible to add 5 meters plus 2 seconds. You simply can't do it. It can't be done. So anytime we're adding things or subtracting them, we just have to have the right units. If we find we're doing some math and the units are different and we're trying to combine them or subtract them, we've made a mistake. We can't do it. So anytime we get to the point where we're breaking this rule, we're simply wrong, right? And we should know that, and we should be able to go back and figure out what it is we did wrong and make it right. Now, really what this video is mostly about is when we're multiplying and dividing, multiplication and division, right? Because there we use what I call unit analysis. And unit analysis is a process for us to check the unit. So I'm going to show you this in a series of examples. And the first one for this is, let's say that we have 5 meters times 2 seconds divided by 4 meters. Let's say we do that now, divided by 10 meters. We'll do it. We'll keep the math simple, and we'll just make sure that we look at the units. So we're coming up with a really simple example. We'll get more and more complicated as we go, just to make sure that we understand what we're doing. All right, so 5 meters times 2 seconds divided by 10 meters. So when I do unit analysis, I call it the train tracks lots of times. And lots of times when you're doing work, I'm like, hey, where's the train tracks? And this is what I'm talking about. So first thing I do is I draw a horizontal line. Now this horizontal line is the only line like this that we need to draw. And we'll see it with other examples, but units are either above the line or below the line. I don't make any more lines. This is it. So first value goes on top because it's the first value. The units with it stays with it. So it's 5 meters. I draw a vertical line before I put in my next value. I'm multiplying by 2 seconds, and then I'm dividing by 10 meters. So every time I'm multiplying, the number goes on top. Every time I'm dividing, the number goes on the bottom. And I just have to follow that rule, right? Which mathematically is perfectly fine, because when you divide by a number, it's the same as multiplying by its reciprocal. And that's really what we're going to do, is we're going to put reciprocals in here. But with that said, I am multiplying by 2 seconds. So the 2 goes on top, second stays with it. I'm dividing by 10 meters. So the 10 goes on the bottom and the meter stays with it. Now, when I look at this, 2 times 5 divided by 10 is 1, right? And this isn't really how we do the math, right? The math you could just use a calculator for, but it does lay it out. And then I look at this and I have meters on top, I have meters on the bottom. So as I look at this, I have 2 units of meters, one on top, one on bottom. So those just cancel out. Meters are gone. What am I left with? I'm left with 1 second. There is my answer. When I multiply and divide in this way that we listed, my answer is 1 second. So there is my first example. Let's look at a different one. Let's make it a little more complicated. Let's say we have a speed 4 meters per second, and we're going to divide it by 2 kilogram per meter second. I'm going to say it right. So we're going to divide it by 2 kilogram meter per second. One more time. We're going to divide it by 2 kilograms per meter second. There we go. And then we're going to multiply by 5 meters per kilogram. That's good. We're going to multiply it by 5 meters per kilogram. Now, using the unit analysis is a little more helpful to us. I'm multiplying. Well, it doesn't matter what I'm doing. First number goes on top. The meter stays with it. Now, where do I put the seconds? Well, again, these lines here, I'm never going to draw again. This line, and this line, they're all replaced by my horizontal line right here. So that's what I'm replacing it with. So I'm not going to have fractions inside fractions. It is 4 meters per second. Vertical line for the next one. I'm dividing, so the 2 goes on the bottom. Kilogram stays with it. And then where do the meters and seconds go? I'm not putting them down here. That would be wrong, right? I am simply filling in the other space. So I know where the number goes. The units that are with that number stay with it. The other units fill in the other space. 5 goes on top because I'm multiplying. Meter stays with it. Where do the kilograms go? They fill in the other space. So this is how I'm setting it up so that I could see what's going on. Now, doing the math, I can do all the tops and then do the bottoms. I can go left to right. I have choices of how I want to do the math, right? I can do 4 times 5 divided by 2 works out to be 10. I can do 4 divided by 2 is 2 times 5 works out to be 10. The order you do multiplication and division doesn't make a difference. As long as you do it all, then the order doesn't matter. Either way, I get 10. Now it's 10 what? Well, as I look at this, I have a unit of seconds on the bottom, which is going to cancel out a unit of seconds on the top. That's the only thing I could cancel out. I have a bunch of meters, but they're all on top, so they're not canceling out. I have a bunch of kilograms. They're all on the bottom. They're not canceling out. So as I look at this, I have 1, 2, 3 units of meters, so it is cubic meters, which is certainly a common measurement. That's volume lots of times. And then on the bottom, I have kilograms and kilograms, so it's per kilogram squared, right? And it's going to be hard to see these things unless I set it up this way. So the train tracks allow me to see all the units that I have so I could keep track of them. Let's do one more on this slide. Let's do 7 kilogram meter per second squared times, let's see, 10 meters per kilogram divided by 5 seconds per meter squared. There we go. 7 kilogram meter per second squared times 10 meters per kilogram divided by 5 seconds per meter squared. Same type of setup. Draw my horizontal line. First number goes on top. And again, I'm filling the top and the bottom. The 7's on top, so the kilograms and meters stays with it. Where do the seconds go? They fill in the other space. Draw a vertical line to separate it. I'm multiplying, so the 10 goes on the top. Meter stays with it. Kilograms fills in the other space. And now I'm dividing, so the 5 goes on the bottom. Second stays with it. Meter squared fills in the other space. So now I've got some pretty complicated units, right? But still, as I look at this, I have kilograms top and bottom, so they cancel out. 7 times 10 is 70. 70 divided by 5 is, let's see, 14. And then let's look at the units. So I got a lot of meters. They're all on top. 1, 2, 3, 4. 4 units of meters, so it's meters to the 4th. On the bottom, kilograms cancel out, so I don't have to worry about those. I have 1, 2, 3. 3 units of seconds, seconds third. So there we go. There's 2 more examples. Now, for both of these, the units don't make much sense because I just kind of pick measurements at random and say we're going to multiply them together, but they're still right. Now, what are some units or conversions that we should know? So we're going to say some common units. And what we have out there is we have a lot of things that are common units in the metric system, and they were made just because people didn't feel like writing out the combination of fundamental units, right? We have things like measuring force. We tend to measure force in newtons. Why do we use newtons? Because it's easier than writing a kilogram meter per second squared, right? But we have to know that conversion. 1 Newton equals 1 kilogram meter per second squared. And then we're measuring energy. Energy we tend to measure in joules. And 1 joule is 1 kilogram meter squared per second squared. And then 1 watt is 1 kilogram. Let me write that one correct. 1 joule, 1 kilogram meter squared per second squared. I said it right. Let me write it. And then a watt is 1 kilogram meter squared per second cubed. So there are some of our common units. Later on, we're going to get into other ones like a volt. Well, a volt is 1 kilogram meter squared per second squared coulomb. So again, as we get more and more into measurements, the units get more and more complicated. So there's measurements that we use over and over and over again. We tend to have given them another name for their units, right? But they still just equate to some combination of our fundamental units. All right, along with these common units, there are some conversions that we should be aware of. And these are just ones that will come up with lab, right? The metric system has all kinds of different units, but to be honest with you, people don't use all of them. But we tend to use centimeters. Centimeters is a common unit, and to go from centimeters to meters, because again, all answers are always in meters. We know there's 100 centimeters in a meter. Grams is something that we're commonly going to use, and to convert that to kilograms, which is the units we always want to be using, there's 1,000 grams in 1 kilogram. And I guess millimeters would be another one. I don't know how many times we measure things in millimeters in class, but it's still a common measurement where there's 1,000 millimeters in 1 meter. So these are some conversions that we should know, right? Because we'll definitely take measurements using centimeters and grams. We'll have to convert them before we use them. So our answers are all in kilograms, meters per second, and seconds. All right, so let's do something more complicated with this. Let's do another calculation. And let's say that we are going to multiply 5 meters per second times by, there we go, times by 6 kilograms per meter second. And then we're going to divide by 10 centimeters per gram. Let's say we have that. Horizontal line, 5 goes on top, meter stays with it, seconds, fill in the other space. I'm multiplying, so the 6 goes on top, kilograms stays with it. Meters and seconds, fill in the other space. I'm dividing, 10 goes on the bottom, centimeters stays with it, grams, fill in the other space. So I have this set up here right now. I can do the math. 5 times 6 is 30, divided by 10 is 3. I look at this, nothing's canceling out. So what do I have? I have a kilogram, gram, meter. Oh wait, meters cancel out. See, now just by setting this up, I could see these things because I'm writing at top and bottom. So those are going to be gone. So let's get rid of this. So I have kilogram, gram on top. Meters did cancel out. I have centimeters, seconds squared. Now, technically, this is right. The problem is it's not really useful because I have so many different units in there. I really don't know what I'm talking about. I don't know what I mean when I put all these in. So I'm going to erase my answer. And this is partly why we want to make sure everything's in the fundamental units that we listed: kilograms, meters, seconds, and coulombs, because we don't want answers that make no sense like that. So I need to do some conversions. Right, going back and looking at these conversions, I know that there is 1,000 grams in a kilogram. I know that there's 100 centimeters in a meter. I really want to stay away from moving the decimal point. I know In middle school, when we learn conversions between those, it's like, oh, move it 2 places to the left, move it 1 to the right. We're going to do it all on the train track, so we don't have to think about it too much, right? The more that these train tracks can help us, the easier it is. So my goal is to get an answer and get an answer that's just in the units that I want, kilograms, meters, seconds, and coulombs. And that means I need to get rid of centimeters. I need to get rid of grams. So I need to put my conversions in a way to get rid of them. I have centimeters on the bottom. So next time I use centimeters, I'm going to put it on the top so that centimeters cancel out. What's left over after that is just what's left over, right? But my goal is to get rid of centimeters right now. So I know that there is 100 centimeters in 1 meter, right? And I can do this mathematically because I'm essentially multiplying by 1. These are the same thing. 100 centimeters is 1 meter. When I do it like that, centimeters cancel out. Now, what happens to meters doesn't really matter to me right at the moment. They're just going to be what they are. But I'm going to get rid of the things that I don't want, and I don't want centimeters. Now I know there's 1,000 grams in a kilogram. I have grams on top, so next time I write it, I need grams on the bottom, and 1,000 grams equals 1 kilogram. So grams cancel out. So now I'm at least in the units that I expect to be in, right? My number's not going to be the same anymore. I'm going to have 5 times 6 divided by 10 times 100 divided by 1,000, right? I can try and cancel some stuff out ahead of time, but to be honest with you, I tend to just do the math left to right. So that's what I'll do. I'll just do 5 times 6 divided by 10 times 100 divided by 1,000. And I get 0.3. And now my units, well, I've gotten rid of all the units I don't want. And now I just have to deal with what's left. I have a kilogram and a kilogram on top. So I have kilogram squared. On the bottom, what do I have? I have 1 unit a meter right there. And I have 2 of seconds, so seconds squared. So the answer is 0.3 kilograms squared per meter second squared. All right, I'm going to do just one more example so we could see. And while I'm writing it, let me just say one other thing. Right? Unit analysis does two things for me, which is why I think it's so important. One, it allows us to check the units, which is the main reason we do it. So when you do calculations like this, when you get an answer, it should tell you, do these units make sense? Because it's hard to tell if the number makes sense lots of times, right? But the units, right, if I got an answer of kilograms squared per meter second squared, first thing I'd be doing is like, this doesn't look like any unit I know. Must be wrong, right? Lots of times these answers should work out to be these units: kilogram meter per second squared, kilogram meter squared per second squared, kilogram meter squared per second cubed, so on and so forth, right? These 4 that I list, these are very common ones. So if I'm calculating a force, I expect the units to work out to be the unit for force, kilogram meter per second squared. So when we get odd ones that don't match up with units we're used to seeing, then we have to take a step back and say, okay, am I calculating something different that I've never calculated before, or am I just wrong, right? And lots of times it's just wrong. The other thing that it does for us, though, is it allows us to see our work in a more organized way, right? Lots of times when people struggle with math, part of the issue is they're just not showing their work carefully enough. So they come up, they have some questions, and I start asking questions, right? We have a problem, we're working on it, and someone's like, hey, Mr. Cormier, I don't really get this. I'm like, let me see your work. And I start asking questions like, hey, what's that represent? Hey, what's that number mean? And then it's like, well, I don't remember. I'm not sure. And I'm like, well, what did you do here? And everything's just hard to follow. And I'm trying to follow it. And, you, the student, trying to follow it. And then we're both kind of saying, I don't really know what we did here. I forget, right? It's because the work's unorganized. So unit analysis allows you to organize the work, right? Which is why it's required on all labs and most exams, right? And the big thing is I can spot it very quickly, and I can then check it very quickly, right? As soon as I find the train tracks, I'm going right to them. I'm checking the units. I'm looking at the math, and it's all organized in a way that's easy to follow. So not only is unit analysis important because it allows you to check the units, it just allows you to organize everything, right? And organizing everything is a great, great thing to do. Units squared per gram. And we'll tack one more on there. We'll multiply by 5. Let's see, 5 millimeters per gram again. Yeah, that works. All right, train tracks, I set it up. 10 kilogram meter per second squared, 5 seconds per kilogram, divided by 25 minutes squared per gram, and then I am multiplying by 5 millimeters per gram. Now, as I'm setting it up like this, I look at it and say, okay, I've got minutes, I got a conversion there. I got millimeters, I got a conversion there. I have grams, I got a conversion there. But as I set up with the train tracks, I see one thing that jumps out for me. So first of all, I have a kilogram on top, I have a kilogram on bottom. Those are going to disappear. I also have a gram on top and I have a gram on bottom. Those disappear. So before I even do the conversion, I've already gotten rid of one thing that I would normally have to convert. So that's kind of nice for me, right? And because I set it up with this train tracks method, I can see that. Now I've got to deal with minutes and I got to deal with millimeters. So I'm going to deal with the minutes first. Minutes are on the bottom. So next time it cancels out, it's on the top. So 1 minute is 60 seconds, and that's good. And if I look at it though, 1 minute is 60 seconds. I have 1 minute on top and it's minutes squared on the bottom. So this didn't cancel out everything. This canceled out one of the minutes. So that tells me, hey, I've got to do this twice. 1 minute is 60 seconds. And this is going to cancel out the other one. So all minutes are gone, and I'm left in seconds, which is good because seconds are an acceptable value for me. I keep going with this, so let's see. This second, well, this second can cancel out in lots of places. I have 1, 2, 3, 4. I have 4 units of seconds on the bottom. This is going to cancel out one of them. It doesn't matter which one I pick, right? I'm going to pick this one. How many am I left with? I'm left with 3. If I picked one over here, I'd still be left with 3. Either way, I cancel out one of the seconds that are on the bottom. And now I have all the minutes gone. There was minutes squared here, so 2 different minutes that we have to get rid of, and we've done it twice to get rid of both of them. And then what do I have left? I have millimeters still. I have millimeters still, so I need to get rid of millimeters. It was on top, so next time I write it, it's going to be on the bottom. And I know I have 1,000 millimeters in 1 meter. So I have millimeters top and bottom. They're going to cancel out, which was the whole point, right? That was the goal of this. And now what do I have left? So I'm going to use my highlighter, and let's see. I have, that's an ugly color. Here we go. I have seconds. I've got all of those on the bottom, so I know my answer has 1, 2, 3 units of seconds on the bottom. Seconds cubed. And what's over seconds cubed? Well, let's see. I have a meter, and I have a meter, and that's it. So I have meters squared. Now, I didn't get a number yet. I'm going to get it right now, but I know I'm right. As soon as I get to this point, I've checked all the units. Then now it's just plugging in the numbers and seeing, right? So I can just go left to right again. 10 times 5 is 50. Divided by 25 is 2. Times 2 times 5 is 10. So then I have 10 divided by 60. Then I have to do it again, divided by 60 twice. And then I have to take that answer and divide it by 1,000. So this is getting smaller and smaller. So I have a very tiny number because of all these conversions I had to do, but I get 2.78 times 10 to the negative 6 meters squared per seconds cubed. All right, so I did a whole bunch of examples here. All of them are just a bunch of made up numbers so we could see how the units work out. We could also incorporate any type of unit conversions right into this too, right? It's just another train track. You just put another vertical line and do your conversion, put another vertical line, do your next conversion, right? So we could do this all day. I can't really make the problems harder than this. I could just make the problems longer than this, right? So we just keep having to put more and more train tracks into the problem. But that's really it, right? We can organize our work so that we could see everything, and then we could see what units cancel out. So there is unit analysis.